I am live over on Æther Cosmology. If you are tuning in on Space Audits or Æther Cosmology, thanks for being here. And today we're going to talk about Wang, and I would say that he is... People like to write off his generalization of the Sagnac effect in 2004 as if it was an unremarkable experiment and as if he was doing like a parlor trick or something. Some people actually try to give a relativistic explanation for it, and it's not a very satisfying explanation, and they'll do as much as saying it themselves in the papers. They'll say things like, from the perspective of the observer, the effect is not the explanation is difficult, but then they'll show the math with the Lorentz transform. But in any case, this is a lot kind of focuses around that. And if you don't know, Wang in 2004 performed an experiment that showed that the velocity of light is relative to its inertial frame, even if it's in a linear vector. So that would mean that when they tried to measure the orbital motion of the Earth in 1887 in the Michelson-Morley experiment, they would have been able to measure that even after Einstein came along and said that that was technically a linear geodesic. From the perspective of relativity, this is a big problem because it would mean that there's really no way around it. The relativistic explanation doesn't work once the Sagnac effect has been linearized, because they have to try and invoke a rotational vector in order to explain it. So in any case, here's a quote from Wang. Because there is a preferred frame near the Earth, we can identify two different kinds of motion. The motion relative to the preferred frame is a true motion, and the motion relative to the other reference frames is an apparent motion. Now this is in contradiction to what Albert Einstein would say. And so let's get into it. Now, oops. Look at a timeline real quick here. So in 1979, 1980, Wang was in China, and he published, "Has the relativity principle and the special theory of relativity been fully verified by experiments?" And he proposed that maybe it hadn't been, and then he said, hey, why don't we take an interferometer up into a satellite, or like the ISS, and we can do an experiment there, and we can test if the inertial frame gets measured there, and that would, potentially verify or potentially falsify relativity. And then somewhere along the line between 1980 and 1998, he came to the United States, moved to University of St. Paul, and in 1998 he published From the Triangle Sagnac Experiment to a Practical Crucial Experiment of the Constancy of the Speed of Light Using Atomic Clocks on Moving Objects. And this is him talking about a hypothetical theoretical experiment that could be done to using atomic clocks to, see if relativity is accurate. Then in 2000, he published Successful GPS Operations Contradict the Two Principles of Special Relativity and Apply a New Way for Inertial Navigation. So he looks at GPS and how it works. He's talking to people like Ron Hatch and Neil Ashby, or not Neil Ashby, Dean Langley. And he's learning about how GPS works, or he understands it somehow. And he realizes, well, in that case, we could do an experiment to show how linear motion is relative to the relatively measured by the speed of light, and then we could actually use that for like pure navigation. We could find pure speeds we could find our speed through absolute space without having to invoke any other frame of reference. And then in 2000, later in that year, he published Re-examine the two principles of special relativity and the Sagnac effect using GPS's range measurement equation. Again, just going through the same kind of concept about how GPS kind of falsifies relativity. And then in 2002, he got together with Ron Hatch, and they wrote Conducting a Crucial Experiment of the Constancy of the Speed of Light Using GPS. And then in 2003, he published two more papers. So he had been thinking about what he mentioned in 2000 in this paper, and he published first order fiber optic interferometric experiments for crucial test of light speed constancy. So he's starting to propose the idea of linearizing the Sagnac effect, essentially. And then in 2003, he wrote Modified Sagnac Experiment for measuring time travel difference between counter-propagating beams in a uniformly moving light. And so that was when he actually got a fiber optic gyro from the Naval Research Laboratory, and he did a few configurations with the fiber optic gyro to show that the linear motion was measured. And so then that was in 2003, and in January of 2004, he filed the provisional patent paperwork for an interferometric speedometer, patent number 7586587. And so he saw something there, clearly. His experiment was not unremarkable to him. And then in 2004, the Naval Research Laboratory loaned him a fiber optic gyro again, and he performed more experiments to further explicitly linearize the Sagnac effect. And he published the paper called Generalized Sagnac Effect. He kept publishing on these topics, and he actually did another experiment. He published test of the one-way speed of light and the first order experiment of special relativity using phase conjugate interferometers. And we'll get into that when we get to the paper, but the idea is that a phase conjugate mirror allows you to actually reflect a wave in the same orientation in which it was received, is my understanding, and then when it comes back, you can actually, because of the way that the interference pattern is reflected, you can actually deduce what the one-way measurement would be, and then you can use that interference pattern to then find the one-way, quote-unquote, speed of light, quote-unquote. But in any case, so that was in 2006, and he did the experiment and published that. And then in 2008, he was still thinking about relative motion, and he published Can a Matter Wave Interferometer Detect Translational Speed? And that talks about different ways in which it actually has been shown experimentally to detect translational speed. And then he proposes yet another speedometer, another absolute space speedometer using quote-unquote matter waves. And then in 2016, so this is, 12 years after he's generalized the Sagnac effect, he's still writing about it. He wrote Light Drag Effect of Vacuum Tube versus Light Propagation in Stationary Vacuum Tube. We'll get into that one. It's kind of a crazy name, but it's just him showing a bunch of ways that you could really get down to the bottom of how wrong is relativity. So he's still been thinking about it 12 years later. And then now here we are, another 7 years later, and he wrote Anisotropic Propagation Speed of Light on Rotating Earth's Surface, Theoretical Derivation Implications for Definition of Meter and Crucial Experiment. And actually what he says, definition of meter here, what he means is that if the speed of light is constant, then we can measure a meter by a certain pulse rate of the quote-unquote speed of light. And because of the way that light propagates on the Earth, a meter is actually shorter one way and longer the other way. And that's what he means here by definition of meter. And so he proposes an experiment here that we'll talk about how that could be measured. And basically just, there's still people that will deny even this fact of the anisotropic propagation speed of light. And Wang's just proposing another way that we could hopefully, open their eyes about these things. But yeah, in any case. So that's a timeline. Now let's get into the papers. So in 1979, as I mentioned, or 1980, January 1980, I think was the final publication date, he wrote, has the relativity principle and the special theory of relativity been fully verified by experiments? And he wrote that when he was at the Institute of Mechanics in Academia Sinica in Beijing. And he talks about a suggested new Michelson-Morley experiment in Spacelab. When analyzing the existing experiments used to verify special relativity, it can be seen that they all bear the following common feature. They were carried out at laboratories which are stationary with respect to the Earth, such as Fizeau's experiment, Michelson-Morley's experiment, tests of the increase in mass with increase in speed, and the experiments which show the extension of a lifetime of a decaying moving at high speed, of a decaying particle moving at high speed. And so, I'll just jump to the bottom here. He says, the experiment in Space Lab might also find the shift in interference fringes. This would lead to the failure of the relativity principle and the special theory of relativity. And he's also said, so I will read this actually. There's no reason to conclude a priori that the experimental results in another inertial system will certainly confirm the relativity principle, since up to now, no such experiment has been performed. So he was thinking about this back when he was in China in 1979, 1980. And then at some point, he came over to America, and like I said, he went to St. Paul, Minnesota. And in 1998, or St. Cloud, it's St. Cloud State University. Correction there. That's in St. Cloud, Minnesota. But he published From the Triangle Sagnac Experiment to a Practical Crucial Experiment of the Constancy of the Speed of Light using atomic clocks on moving objects. According to the Triangle Sagnac Experiment, objects that are between point A and point B that are moving in circular motion, the travel times for light or radio signals from A to B and from B to A are different. The difference, lambda t, i.e. the Sagnac effect, and then let's skip down to my highlights, I won't read the whole thing. The Sagnac effect exists whether the radius of the circle is small as only a few centimeters in fiber optic gyroscopes or as big as 20,000 kilometers, example given in GPS. So he's saying whether you're on the quote-unquote rotating Earth or whether you're in a small circle like when Georges Sagnac did the experiment in 1912, there you're going to get a relative Sagnac effect. And if we mount an atomic clock and a signal transmitter and receiver on each of two moving objects at the same speed in a circular motion, we will find such a time difference. And we'll get into that, but he essentially talks about airplanes and helicopters doing this along with the assistance of stationary satellites that would send and receive signals to these crafts, but we'll get to that in a little bit. And then he says, easy to detect with current technology, verification of the Sagnac corrections in GPS. So it can be used as a verification of the Sagnac corrections in GPS. And a theoretical problem arises when these two objects change their paths to a straight line. Would the time difference still exist? Then it contradicts the principle of the constancy of the speed of light. Or does the time difference jump to zero? The result of the experiment will be of great interest. So essentially, in this paper, he goes on to suggest two different experiments. He says we could have two airplanes with atomic clocks, a transmitter and receiver on each. Both planes fly in a circle, and the Sagnac effect is measured, and then both planes fly straight. Will the Sagnac effect still be measured? And then he wants to use two helicopters with atomic clocks. And he'll have a transmitter and receiver on each. Both helicopters will hover above the Earth, and Earth rotation will be measured. Then both helicopters will fly forward. Then both helicopters will fly backward. And then you can look at the speed of light differential between those two directions, and you can know that those helicopters only moved in linear motions, and then that, you could derive potentially some conclusions about, it would theoretically contradict the principle of relativity. And this is from the paper, either the time difference still exists or the difference disappears. The speeds of light are different in different directions, therefore it would so if the former happens, the speed of light are different in different directions, therefore it will contradict the principle of the constancy of the speed of light. And it would reveal whether or not the speed of light is constant in a reference frame moving translationally relative to the Earth. And because of the practical and theoretical significance and its relatively easy implementation, we hope the proposal will become a reality in the near future. Hey, do you guys think it became a reality in the near future? It didn't. So, successful GPS operations contradict the two principles of special relativity and imply a new way for inertial navigation. That he wrote this one in 2000, and that was when he was in St. Cloud, and he proposes a practical and crucial experiment. Does someone chime in? Oh. All right. So, anyways, a practical and crucial experiment in which What's up?
It's Jackie. I think she's hot micing.
Oh, gotcha. All right. So to verify this experimentally, a practical and crucial experiment in which no clock synchronization is required, although simultaneity is the key of GPS operations, and the relativity of simultaneity of special relativity disagrees with the basic operational principle of GPS. So we can use it to check whether or not the propagation time changes in different frames. It can be predicted that the crucial experiment will give a result contradicting the two principles of special relativity. The crucial experiment can be simulated easily with GPS simulators. And then he says, furthermore, the falsification of the two principles of special relativity and the calculations based on the GPS equation illustrate a new way for inertial navigation, measuring speed directly. So this is when he has his light bulb moment in this paper. While he's writing about GPS and how GPS contradicts special relativity, he realizes, like, well, we could make a prototype of a speedometer based on this. You know, we could do an experiment, and then we could use that to make a speedometer. So he gives his crucial experiment right here. He talks a lot about crucial experiments, if you haven't noticed. So he says, in the books about special relativity, the most commonly cited example about the relativity of simultaneity is the example about the railway platform and the moving train. It says that two events, example given the two strokes of lightning A and B, which are simultaneous with reference to the platform, are not simultaneous with respect to the moving train and vice versa. But now GPS receivers have been utilized extensively on railway platforms and moving trains, and lightning at two different places, A and B, conceptually is the same as the emissions of GPS signals from the two satellites or two DGPS stations. Both the GPS receiver on the railway platform and the GPS receiver in the moving train would both acknowledge the two events, the emissions of the signal, to be simultaneous. Without this basic acknowledgement, the GPS receivers cannot function at all. And then he has basically it's like the train platform, but with GPS receivers. And then he has his new idea for inertial navigation. Measuring speed directly. It is well known that inertial navigation utilizes an accelerometer for linear acceleration and a gyroscope for rotation. Linear speed is determined by integrating the accelerometer output and cannot be measured directly. But from the calculations given before, we understand the principle of relativity could not be true. It also tells us that it is possible to distinguish one inertial frame from another inertial frame. Speed relative to the ECI frame can be measured directly. In fact, we can design a prototype of a new speedometer immediately from the crucial experiment. And so there he has a couple of prototypic designs. He's got this version with the atomic clocks, and then this version, which would be an improved version because you would get more precision. And actually, when he actually made the patent, we'll get to that, it ended up looking a bit different than these. So, because there's a preferred frame near the Earth, we can identify two different kinds of motion. The motion relative to the preferred frame is a true motion, and the motion relative to the other reference frames is an apparent motion. And that was the quote from earlier that I showed, and I think it's kind of a central thesis to what he showed with all of his experiments, actually, in my opinion. So then in February 2000, he published Re-examine the two principles of special relativity and the Sagnac effect using GPS range measurement equation. And so this is him talking more about, the same thing essentially, that successful GPS operations are based on a basic equation, the range measurement equation. The correctness of the equation leads to the incorrectness of two principles of special relativity: the principle of relativity and the principle of the constancy of the speed of light. The Sagnac effect can be fully interpreted by this equation. The Sagnac effect is a non-relativistic effect. It contradicts the basic operational principle of GPS. So then he talks about a practical and crucial experiment that does not require any clock synchronization, contradicting the two principles of special relativity. And we will re-examine and reconstruct special relativity starting from its foundations, or we should construct the experiment, the crucial experiment. So, He talks about, compared with a stationary receiver in Earth's under an inertial frame, a receiver moving relative to ECI will receive the signal from the source at a different time. The Sagnac correction is a correction added in the calculation when we use the range measurement equation. In fact, if we use the range measurement equation in its original meaning, i.e., range being the distance in the Earth's under inertial frame between the source at the transmission time and the receiver at the reception time, no correction is needed. The Sagnac effect is included automatically. So there is no Sagnac correction that you have to do with range measurement equations because it's just inherent in the equation itself. Like, that's literally how it works. It looks at how long it took to get to that destination, or it looks at the time differential there. And so then that is, although there is a Sagnac effect, there's no need for a Sagnac correction because it's in the equation. But then there's also times where a Sagnac correction must be added in order to compensate for the difference caused if you were to use a different reference frame or a different coordinate system that wasn't adopted into the ECI, essentially. And so then he has a diagram showing this here. I'm not going to go through all the variables of this. But yeah, that's the Sagnac correction in the ECEF. So this is if you don't go into ECI and do the range measurement equation, this is doing the Sagnac correction on the other coordinate system. So we should add that the Sagnac correction, if we use the range measurement equation in a coordinate frame that is moving relative to ECI, or so we should add the Sagnac correction if we use the range measurement equation in a coordinate system that is moving relative to ECI. So if it's not in ECI, you have to do a correction, but at the instant of the transmission. So therefore, the Sagnac effect is not a relativistic effect. Contrarily, it is a non-relativistic effect. So he talks about simplifying the crucial experiment using GPS. When we say the correctness of the range measurement equation leads to the incorrectness of the two principles of special relativity, we mean it not only qualitatively, as we mentioned before, but also quantitatively. The difference between what special relativity predicts and the range measurement equation calculates is an item of VL divided by C for length, or VL divided by C squared for time. GPS has reached unprecedented precision of positioning up to orders of millimeters. Therefore, quantitatively, GPS practices have proved the correctness of the range measurement equation and the incorrectness of the two principles of special relativity. So that was that paper. And now, in 2002, he got together with Ron Hatch, and they published Conducting a Crucial Experiment of the Constancy of the Speed of Light Using GPS. And a quick I liked these two biographies that were present in this paper here. Wang graduated from Beijing University of Aeronautics and Aerospace. He worked in the Institute of Mechanics, Chinese Academy of Sciences. Currently, he works in St. Cloud State University. He has been interested in special relativity, especially its crucial experiments, for a long time, and published several papers on the topic. Ronald R. Hatch. What's that?
No, I said interesting.
Ronald R. Hatch received his Bachelor of Science degree in Physics and Math in 1962 from Seattle Pacific University. He worked at Johns Hopkins Applied Physics Lab, Boeing, and Magnavox before working a time as a GPS consultant. In 1994, same year he published Escape from Einstein, he joined Jim Litton, K.T. Wu, and Jalal Obani in starting what is now Navcom Technology. He has served as a number of roles with the Institute of Navigation, including chair of the Satellite Division. He is currently finishing a one-year term as president of the Institute of Navigation. Ron has received the Johannes Kepler Award and the Satellite Division and the Colonel Thomas Thurlow Award from the Institute of Navigation. He's also a fellow of the ION. He has been awarded 12 patents, either as inventor or co-inventor. Most of the patents relate to GPS. So I would say the guy might know what he's doing with GPS, not to, appeal to credentials too much, but just for the people that care, there you go.
Yeah.
When a GPS receiver changes its translational speed relative to the ECI frame, the speed of light measured relative to the receiver changes. Oh, so that's from the abstract. Otherwise, it is not. So The travel time differences obtained as the airplanes fly in opposite directions are compared. If the travel time difference is the same when the velocity of the airplanes is changed, the velocity of light is indeed constant relative to the moving airplanes. Otherwise, it is not. So this is him and Ron Hatch. They're proposing a crucial experiment using airplanes and GPS. The calculation using the GPS range equation and the results of a real-time kinematic differential GPS test have shown that the constancy of the speed of light, quote-unquote, relative to moving airplanes is not correct. The change of the time difference could reach about 10 nanoseconds for subsonic airplanes and 30 nanoseconds for supersonic airplanes. A new way to measure vehicle speed relative to the ECI frame is what that could possibly lead us to. The reason some do not believe in the constancy of the speed of light relative to a moving observer is in fact that there are experimental facts which indicate there are experimental facts which indicate otherwise, that the speed of light relative to a moving observer is not constant. However, the assertions that the speed of light is constant in just one inertial frame, the ECI frame, really is not what the constancy of light means, because the ECI frame is just part of the range measurement equation, essentially. And so when you have to, when you take into consideration the vectors that are taken, it's already taken into account when you bring things into the ECI frame, essentially, with GPS.
Yeah, that's awesome.
So do we have a principle of the constancy of the speed of sound, because the constant speed of sound, A, appearing in the propagation delay equation? So in this, what he's talking about, he's trying to explain the lack of logic of our assertion about the constancy of the speed of light, or the constancy of C. That would be the speed of light, quote unquote. But the speed of sound is denoted as A. And A does the exact same thing as C in regards to being relative to the speed of its inertial frame. And actually, that might be one of the best ways to explain this to somebody, is that if you know how sonar works, and the fact that you would, I guess you don't really, when you first think of sonar, you don't really think about relative speed, so maybe that's not the best example, but you would always have to take into account your relative speed of your submarine or whatever. If you were sending out sound waves in water, the speed of sound doesn't move slower or fast, or doesn't always move the same speed. Maybe the best example would be a siren driving by you on the highway. There's an ambulance, and then you don't hear it constantly the same speed, you don't hear it at the exact same way the whole time it goes by you. You hear it relative to that car flying by you, and you hear it get louder and then quieter, and you hear actually a little bit of a phase shift as it comes and goes. But we don't have a constancy of the speed of sound, and C does the same thing, so that's what they're getting at here. In fact, when we judge whether the speed of sound is or is not independent of the motion of the observer, the speed of sound is measured in the frame of the observer, not in the frame of the air. From the physics textbook, we can find these. The fact that the speed of light is independent of the motion of the source is not at all troublesome, but it is also independent of the motion of the detector, i.e. but is it also independent of the motion of the detector, i.e. the observer? Certainly, the speed of sound is not. If the detector rushes toward the source, moving with respect to the air, the measured speed of sound increases. So, yeah. And then he has some images here demonstrating this. So this is speed of sound, and then it's got cut off, but this says the speed of GPS propagation, essentially. So it's the same thing. It's relative to the velocity of its movement. However, measured in the frame of the observer and the moving ship, the traveling distance of the sound wave is still the distance between the bow and stern. Oh, so just going back to the start, my bad. So he's talking specifically about sound, and this is the boat example. I kind of glazed over that, my bad. He's talking specifically about the speed of sound on a boat in this situation. But then he's talking about how you'd have the exact same effect with GPS. Hence, we never have a principle of constancy of the speed of sound. Contrarily, we say the speed of sound is not independent of the motion of the observer. Let me take a quick drink of water if you all don't mind. All right. However, for an observer within the system, The distance between the bow and stir is constant. Thus, measured by this observer, the speed of light is not constant. The speed of light is not independent of the motion of the observer relative to the ECI frame. This is what GPS tells us. And so this is still them talking about GPS. The speed of light measured in the ECI frame is always c, whether the receiver is moving relative to the ECI frame or not. When a GPS receiver changes its translational speed relative to the ECI frame, light does not change its speed relative to the ECI frame. Therefore, the speed of light relative to the receiver moving with respect to the ECI frame changes. And then he talks about the Sagnac effect. And I'm not going to read all this. I'll just read the bottom here, because it's kind of crucial. Just to go back, they say we can measure the rotation of the Earth using Michelson-Gill-Pearson, and that's because it's a rotational vector. And they say that that's also what they measure with the fiber optic gyroscope and with the ring laser gyro. But, what these GPS range measurement equations seem to be indicating is that these are like linear vectors, and they would have to claim that that's part of the rotational vector, but that's just unintuitive for a reason, because it's not the natural line of logic that really should be followed, because it is literally a linear vector. But since rotation is not relative, the Sagnac effect can be due to non-isotropic light speed and still be consistent with special relativity. The effect of the movement of the receiver during the transit time of a GPS signal is referred to in GPS system as a one-way Sagnac effect. So there he is, saying it plain and simple. Kind of like I was trying to get explained, but of course he can explain it better than me. And so Ives claimed in 1938 that the effect is not due to rotation, and proposed an experiment in which the light followed a hexagonal path. Ives claimed that the detector could be moved linearly along one side of the hexagonal path and the effect would still be present. Recently, Wang has proposed some first-order interferometric measurements, and their results will show that the Sagnac effect exists not only in circular motion, but also in translation of motion. And then they talk about a crucial experiment. Another crucial experiment. So they are talking about, I'm not going to read through all of this here, but essentially they talk about using GPS receivers and GPS transmitters and GPS receivers, and then they put them on these helicopters, and then after that they want to do it on airplanes as well. And I like this illustration is, I think, one of the best here. So they're talking, essentially, after they boil it all down and they go through all the caveats of how relativity would try to weasel their way out of it, this is the diagram they came up with the crucial experiment, the simplified version. So you have these two airplanes. They both have a receiver and a transmitter. And then you have these two GPS crafts out here. And they're both sending signals to both of the aircrafts. And then both of the aircrafts are going to fly one way. And then they're both going to turn around and fly the other way. And then comparing if there's a Sagnac effect on both airplanes going both directions, you can then deduce whether or not there was a purely linear vector measured there going both ways, one way or the other, especially because you can do the differential of the one way versus the other, and you would have the signal from both GPS going to both craft or both airplanes in both directions. So it would be a very definitive experiment. And so then they have their conclusions here. Talking about the quote-unquote speed of light, this isotropy of light speed, or really electromagnetic waves propagation, or they would say speed, the isotropy of light speed relative to the chosen frame is strongly supported by the one-way Sagnac effect. It is clear from the GPS range equation that the motion of the observer during the signal transit time implies the speed of light relative to a moving observer is not isotropic and clearly differs from c due to the receiver motion. This is also evidenced by the JPL space probe equations described by Moyer. The Sagnac effect is caused by any motion of the observer or receiver relative to the chosen inertial frame. Virtually all the measurement error sources are canceled by the multiple differencing involved in the experiment. So this means that the proposed crucial experiment should be capable of easily resolving the fundamental question: is the speed of light constant relative to the receiver, or is it constant relative to the chosen inertial frame? And so now, in 2003, he's going to talk about first-order fiber interferometric experiments for a crucial test of light speed constancy. And he talks about the translational motion so he's talking about the Michelson-Morley experiment, the Sagnac experiment, and from what they learned there, he says the design of interferometric experiment is that it's not only sensitive to linear motion, but also first order and speed. So in order to address this experimentally, it needs two features. It needs to have optical paths and uniform translational motion, and it needs to have paths for light to return without cancellation of possible effects. So he talks about a conveyor-like arrangement and a shearing parallelogram arrangement. Translational motion in these arrangements will lead to an increase in the optical path length and an increase in the travel distance or travel difference, a result falsifying the principle of the light speed constancy. And in my opinion, I would say showing that essentially there would have to be, the implication would be that there would have to be some kind of an ether, or you don't have to call it ether if you don't want, but that's what it is. So this is Sagnac in a rotational vector. This is the kind of the initial Sagnac experiment, or at least conceptually a demonstration of it. And then he talks about kind of cutting that in half, putting some linear segments in, and then also doing this with a parallelogram where you would just move this part. There's two different experiments here. And two arrangements for the first order experiment, a conveyor-like arrangement and a shearing parallelogram. And so here's an image. So this is a typical fiber optic gyro here, right? You would go in through the fiber optic cable, and you come back and get your interference pattern here. But they talk about, his idea is that we can take that and turn it into a fiber optic conveyor. Now, so you think about it here. Wang has been publishing paper after paper after paper about GPS. And he's screaming about light speed constancy or lack thereof. And he's trying, I think at this point he has to be getting some attention, because I would assume that the militaries of the world would kind of know the implications of that. But so now he's proposing it very explicitly. He's already talked about this experiment in at least one other paper that we saw. He talked about this idea. And you would think maybe at that point someone could have loaned him a fiber optic gyro to do the experiment then and there, but he didn't get a fiber optic gyro. And what did he do? He went and published like 3 more papers about GPS, and then he published this paper showing so explicitly, like, here's how we can do it. Here's how we can show that it's linear or rotational only. And if anyone has ears to listen, or, fiber optic gyro to loan, and some nice wave core fiber or air core fiber, then, we could find out. So that's what he's showing here. That's what he's demonstrating, or, yeah. So in this paper, he talks about how the refractive index is not related. So in 2011, Demjanov kind of implies that the refractive index is what causes the periodicity measured by Miller. Now, I know this is a little bit of a different concept, but I do think it's interesting here because, so here's what he says. It should be noted that the travel time difference, sorry, I don't mean to go too far ahead, because I know not everyone knows what I'm talking about when I say Demjanov, but it should be noted that the travel time difference of the fiber optic conveyor is not relative to the refractive index, n. This means that if the experiment were conducted in vacuum, n equals 1, the same result would be expected. Furthermore, the experiment can be conducted with fibers having different refractive indices. If the results delta T2 equals delta T1 or delta T2 is not equal to delta T1 are the same for all fibers, then they should be the same for vacuum also. So we could use the math to find out whether or not the refractive index is what's causing, what they would have to, they try to wrap up the classical effects in that somehow with some of the explanations, essentially. Not just Demjanov. Other people do that as well. But so this is the conclusion of that paper. Lorentz contraction, a second-order effect, is not a factor in these experiments. All the technologies utilized in the experiments could be the same as those used in the fiber optic gyro. And then he says at the bottom, a result falsifying the principle of the light speed constancy, or that was what this could give us. So, modified Sagnac experiment for measuring the time travel difference between counter-propagating light beams in a uniformly moving fiber. So really, this is an experiment. And honestly, he's going to linearize the Sagnac effect right here in 2003, along with the helps of Yi Zhang, Aping Yao, and Dean Langley. So he says, a fiber optic conveyor has been deployed for investigating the time travel difference between two counter-propagating light beams in uniformly moving fiber. Our finding is that there's a travel time difference, delta t equals 2v delta t divided by c squared, in a fiber segment of length delta L moving with the source and detector at speed v. Whether the segment is moving uniformly or circularly. So it doesn't just have to be a purely rotational vector. And so here's one diagram they show of one of the configurations here. And so essentially you have a conveyor, you have fiber optic cable going this way, and then you have fiber optic cable going this way. So you have two linear motions. You do have a couple of rotational vectors here. And then you have, at the same speed, you have this pushing the fiber optic gyro along with the conveyor. So it's one motion. It goes this way, and this moves with it. And this is where you do your emission and detection, or it emits and detects from here. And what do you know? Here's what they found. The phase shift of light proportional in a moving fiber. The speed of the fiber length is proportional to the phase shift, aka linearized Sagnac effect, aka what happened in 1887, boys. Well, we didn't measure any linear motion, so maybe we're not in motion. Maybe Albert Einstein was wrong. The travel time difference of two counterpropagating light beams in moving fiber is proportional to both the total height and the speed of the fiber, regardless of whether the motion is circular or uniform. The travel time difference is 2v delta L divided by c squared. We thank Robert Mueller of the Naval Research Laboratory for technical assistance in the Naval Research Laboratory for the loan of the fiber optic gyro. So, the Naval Research Laboratory thought it was interesting, caught their attention, and then what do you know, right after that, so the patent got accepted in 2009, September of 2009, but it was only a few months later that Wang went and filed the provisional patent. Him and Yi Zhang and Aping Yao filed the provisional patent for a speedometer based on interferometry. And here's the patent. A standalone speedometer directly measuring the translational speed of a moving body comprises a source-emitting two-spaced light beams with which interfere with each other, mirrors or beam splitters changing directions of propagation of light beams, and a detector measuring the phase difference of light beams. Compared with the phase difference when the speedometer is stationary, the detector measures a first-order change of the phase differences, which indicates the motion speed. And here's a image, one of the many illustrations of how this could be deployed. And this is actually a double-sided, it's essentially like a laser chamber that emits a wave in both directions, so you can have the same phase going outwards in both directions. And so it's a speedometer, and it's a method of directly measuring the translational speed of a moving body. And then, Later on that year, he published the paper titled Generalized Sagnac Effect. Him, Yi Zhang, Aping Yao at St. Cloud State University. And so this is from Robert Bennett in his 2014 paper, A Landmark Experiment, the Linear Sagnac Test of Ruyang Wang. Belief that the Sagnac test of 1913 only applied to rotational motion was discounted when Ruyang Wang found the same results for linear motion in 2004. The Sagnac result has never been credibly explained, despite its wide application in modern technology. In turn, the Wang paper has been virtually ignored the last 10 years. Analysis of Wang's result in the conveyor and lab frames with the premise of Æther drag logically leads to the identification of preferred motion and an absolute frame of reference, the earthbound laboratory frame. So here's the paper, Generalized Sagnac Effect. Light propagation in a light waveguide loop consisting of linearly and circularly moving segments. That's what the experiments were conducted to study. We found that any segment of the loop contributes to the total phase difference between two counter-propagating light beams in the loop. That means whether it's rotational or not. The contribution is proportional to the product of the moving velocity v and the projection of the segment length delta L on the moving direction. It is independent of the type of motion and the refractive index of the waveguide loops. The findings includes the Sagnac effect of rotation as a special case and suggests a new fiber optic sensor for measuring linear motion with nanoscale sensitivity. So he says here, the Sagnac effect shows that two counterpropagating light beams take different time intervals to travel a closed path on a rotating disk. The travel time difference between them is delta t equals 4a, omega, divided by c squared. Any moving path contributes to the total phase difference between two counterpropagating light beams in the loop. The finding also suggests a new fiber optic linear motion sensor having nanoscale sensitivity, which is much more sensitive than any existing linear motion detectors. And there is, yet again, another fiber optic linear conveyor. So we have, it's very similar to the other one, two linear motions, fiber optic gyro moving with it, and you would just boop, boop, everything moves at once. You get one motion here and one motion here. And it gets measured. The linear portion gets measured, directly proportional. And the same thing here. You've got your source gets split. So you got it going both ways. And as it's traveling through here and coming back to the detector, as both beams are going to come back to the detector through here, this moves. So you actually have it going through, and then this moves, and then you detect the phase difference when that moves. This would be delta L. The length, this length here is what is getting moved, and that's what they measure from. And so according to our experiments, the contribution is independent of the refractive index of the waveguide, and the motion of the segment can be either linear or circular. The Sagnac effect of rotation as a special... So this general conclusion includes the Sagnac effect of rotation as a special case. In fact, the Sagnac result can be derived from this equation by assuming a circular motion of the loop and using Stokes' theorem. This generalization provides a design principle for a new fiber optic linear motion sensor. This nanoscale sensitivity linear motion sensor can detect very small relative motion appearing in an accelerometer, which is important in navigation and seismology. The common design of an accelerometer is a spring mass system. Improving the sensitivity of an accelerometer requires improving the sensitivity of detecting the linear movement. It can be foreseen that an accelerometer using a fiber optic linear motion sensor combined with the fiber optic gyroscope may be beneficial for navigation. This is the conclusion of the paper. And so, yeah. And then at the end, thanks Dean Langley for the useful discussions and help. And we thank Robert Moeller of the Naval Research Laboratory for technical assistance and the Naval Research Laboratory for the loan of the fiber optic gyro. So, on a remarkable experiment, I don't know. Naval Research Laboratory thought it was pretty interesting twice in a row. And, you can say what you want about the source that he was published from, because I've heard people try to smear the publication source. But I want to hear... If you're going to try to refute this, I would like to hear about what your contention is with his methodology with his results, not, just smearing the source, especially because of how thorough he was and how many experiments he did and how explicit he was with his math. So, moving on, that was what he did in 2003, 2004. Very massive. It's very direct. I mean, honestly, you go back to 1912, that should have been the end of it. When George S. Saniac first did show the Saniac effect in an interferometer, that should have been the end of it. We should have known, okay, well then they definitely didn't measure any motion in 1887, and the Earth's not in motion. And however hard that is for us to grasp, it's the truth. So, they should have figured it out back then. And the fact that they didn't figure it out back then tells you what kind of world we're living in. And the fact that, this is the cognitive, people have embedded this into their head. And it's not, it's been experimentally proven in front of their faces, and then they will still pretend like they didn't see it. So moving on now, in 2006, Wang is not done. He didn't end it there and stop talking about relativity. Oh, unremarkable experiment. I'm done with my circus trick, or I'm done with my little clever trick to trick everybody into thinking relativity is fake. Now I can go, actually do something productive with my life or something like that. No, he kept writing about it. So obviously he thought he had found something, and I don't think he would have written so many papers about GPS if he didn't think that was showing something either. And I don't think Ron Hatch would have wrote a book about it, the same guy that had to fix GPS. But in any case, I digress. So this paper is called Test of the One-Way Speed of Light and the First Order Experiment of Special Relativity Using Phase Conjugate Interferometers. So some people are talking, oh, well, that's still a second order measurement with the your waveguide loop, because it's in a loop and it's relative to itself or whatever. It's whatever kind of, I don't even feel like trying to explain the arguments that people will make, in that they try to say that because it's two different portions of fiber that are traveling in opposite directions relative to each other, that somehow, because those are relative to each other, that you can invoke them as a placeholder for absolute space to do your geometrically convenient calculation to write off the direct proportional velocity that you measured in your interference pattern right in front of your frickin' face. But in any case, with a Michelson interferometer using a phase conjugate mirror, it reverses the uniform phase shift in a light path. So we can conduct a first-order experiment of special relativity. Utilization of the phase conjugate mirror changes the basic concepts of an interference experiment. Placing a conventional partially reflecting mirror just in front of the phase conjugate mirror at the end of the light path, we can test the isotropy of the one-way speed of light in a system moving uniformly in a straight line and conduct the one-way Saniac experiment. According to the reported phase conjugate Saniac experiment using a segment light path, we can expect that a phase shift is the one-way, I'm not going to read, or so, phi, I believe, equals 4 pi VL divided by C lambda in the one-way Saniac experiment with the length L and the speed V, even in an increasingly larger radius of the rotation. Based on these and the experimental fact of the generalized Saniac effect, it is very important to examine whether it is the same phase shift for the test of the one-way speed of light in the first-order experiment using the phase conjugate mirror in a system in a straight line and uniform rotation. Sorry, I'll just move on here, because this is a pretty cool experiment. Sorry if it's a little technical, but what he's saying here is essentially when they're measuring interference patterns, the waveform of the light is how they measure that. And so when you can use a phase conjugate mirror to reflect the waveform exactly as it was received, it'd be like maybe one way to think of it would be like if you take those there's those like toys for kids that have a bunch of nails in them. It's like a piece of plexiglass with a bunch of nails in front of it, and you can put it up to your face and it like imprints your face on it. I don't know if anyone knows what I'm talking about, but it's kind of like that. It'd be like it comes down and it hits the phase conjugate mirror, and then it keeps that imprint as it goes back towards where it came from. And so because of that, they would be able to compare that result to the result that didn't come from the phase conjugate mirror. So using a standard mirror and doing the calculation of comparing those to each other, they can then deduce what the one-way speed of light, looked to have been. So the utilization of the nonlinear optical properties brings a magnificent change to the interferometers, the phase conjugate mirrors, and they have an important property of phase reversal. So the experiment utilizing the phase conjugate interferometer can be first order. We can have a one-arm phase conjugate interferometer, and because these experiments are first order, the sensitivities of the experiments are very high. The above derivations are based... so let me just go down to my highlight. The two first-order terms in the Michelson-Morley experiment no longer cancel each other, but augment each other. Then we will have a first-order experiment. Additionally, changing a positive phase shift to a negative phase shift is what some phase conjugate mirrors can do. Therefore, if we conduct an experiment with the phase conjugate Michelson interferometer shown in Figure 4, the two first-order terms will augment each other, neglecting terms of order higher than the second. So you can just do you can do the calculation to derive the first order, essentially, or it would be a first-order measurement. More generally, Lorentz's conclusion that the interference experiments cannot detect the first-order experiments is not true for a phase conjugate interferometer because the possibility of the phase reversal is not considered. So Lorentz was wrong because he didn't know about phase conjugate mirrors, essentially, is what Wang is saying here. And so they're talking here, showing the demonstration. You'd have the phase conjugate mirror, you'd have the conventional mirror, and then you would go here, and then you would go here, and then you'd detect the difference at the detector here. And that would allow you to detect the quote-unquote one-way difference. And then you could do a rotation or a 180 and do it again. So the Sagnac effect is fully verified experimental fact with numerous applications, including highly precise fiber optic gyroscopes that are widely used in navigations. However, the arguments about its implications have never stopped, and it is called an unsolved fundamental problem in physics. And I highlighted that in red for a reason, because people try to pretend like this is easily explainable. Relativity's got it all on lockdown. Don't worry, you can't even have a GPS satellite without relativity, dude. You can't even, the Sagnac effect is proof for relativity, dude. Well, not really. Like physics, it's an unsolved fundamental problem in physics. I would call it unsolvable unless, of course, you want to use some kind of crazy machine learning to derive some kind of backwards compatible framework or something. But, yeah, I need just one moment to take a drink of water here. All right, so Sagnac effect is... So a remarkable feature of the Sagnac effect is that all other effects related to the rotation, example given the centripetal force, will approach zero when the radius of the circular motion becomes increasingly larger, while the speed of circular motion keeps constant. However, the Sagnac effect will not approach zero, but a finite value. When the radius of the circular motion becomes increasingly larger, the circular motion approaches the linear motion, and if the Sagnac effect still exists, the time difference still exists. So he's kind of pointing out what I would say is common sense, which actually to me confused me for like a whole year trying to figure this stuff out. Why is it sometimes okay to measure the light speed, sometimes not okay to... It's in a circle, it's going in a rotation. Well, isn't the orbit a rotation? Wait, what? Like, it's all so confusing. Well, it's because it's their explanation is confusing. Their explanation is not logical. That's why it's confusing. So, because, just like your intuition would tell you, just like common sense would tell you, that the circular motion approaches a linear motion. And like even if we were on a rotational Earth, the GPS range measurement equations would still be linear. Like it's still a linear vector. And the time difference is directly measured. So, generalized Sagnac effect. A segment in linear motion contributes a phase shift. Not only the fact that it contributes a phase shift, not only is a deduction from the phase conjugate Sagnac experiment, which we just described, but it's also based on the experimental fact of the generalized Sagnac effect. So he's going back to what he talked about in 2004. He's saying that in combination with this, now you guys are done. Like, you tried to say it's because of this weird relative crap. You tried to say it's because it's a closed loop. And that you're not getting a one-way direction. It's still a second-order measurement, and so we're not going to look at the fact that it's the directly proportional linear velocity. Well, he's showing you here, okay, guys, well, we just double-checked it, and we looked at the one-way velocity, and it was right, okay? Like, generalized Sagnac was correct, so there you go. So the importance of the rest of the test of the one-way speed of light can never be overestimated, because the isotropy of the one-way speed of light not only is the foundation of the principle of the constancy of the speed of light, but also is the core of the problem of simultaneity. It was stated by Einstein that light requires the same time to traverse the path for the A to M as for the path B to M, is in reality neither a supposition nor a hypothesis about the physical nature of light, but a stipulation which I can make my own free will, or which I can make of my own free will, in order to arrive at a definition of simultaneity. So, and M in that, in the context of that, M was the midpoint of the line between A and B. So Einstein was just, like literally saying it's a stipulation of what I need. So the test of the one-way speed of light is difficult because the clock type of the experiments has the problem of clock synchronization, and the interference type of experiments has the problem of the closed light path. So sometime it was even claimed that the one-way speed of light cannot be tested by experiments. But according to Wang, it's been done with phase conjugate mirrors. But, he's still not done. He's still thinking about it. Now in 2008, he published, Can a Matter Wave Interferometer Detect Translational Speed? Same crew, Wang et al., Wang, Yi Zhang, and Yiping Yao. And they're saying, based on the Galilean addition of velocities and the de Broglie relation, it is deduced that a matter wave interferometer with slow speed particles, I'll skip to the red highlight here. This expression is exactly the same as the generalized Sagnac effect for light waves found by experiments, except that V is replaced by C. If the possibility is confirmed by experiments, the conclusions will be that there is a preferred reference frame for matter waves, and a speedometer with very high sensitivity is possible. So, what do you know? Maybe we can use electrons or something instead of quote unquote photons. And so he's talking here about, actually it's been predicted since 1975, and it's been shown in an atom interferometer and an electron interferometer. And essentially, it's the same thing as the light wave interferometer, quote unquote. It's proportionally the same as the Sagnac effect, actually. It would seem that detecting translational speeds using a matter wave interferometer having slow speed particles is impossible because it violates the classical principle of relativity. However, we know that the classical principle of relativity is valid for the phenomena of mechanics, i.e. it is based on the particle-like property of matter. It has not been examined by experiments whether or not the classical principle of relativity is valid for matter waves. So he proposed a couple of experiments, a couple more crucial experiments, although he didn't call them crucial. I guess he feels the crucial part's done at this point. But actually he's not. He doesn't, because he proposes another crucial one in 2024 that we'll get to in a minute, or 2023. If the fringe shifts are found by the experiment, the conclusion will be that there is a preferred reference frame for matter waves, that old preferred lab frame. So that was that paper. And then in 2016, he published, him and the crew, or actually, so this is him and some people from the Shanghai Jiao Tong University in Zhengzhou, and they published light drag effect of vacuum tube versus light propagation in stationary vacuum tube. And they present a new way to examine the principle of relativity of special relativity. We select a vacuum tube with two glass rods at two ends as the optical media. The light drag effect of the moving vacuum tube with the speed v is a first order effect, which is independent of the length. However, all analyses have shown that the change of the propagation time interval delta r is caused by the motion of the receiver during the light propagation in the vacuum tube. Thus, the contribution of the glass rods is not the contribution of the vacuum, not zero. So our analyses are solid in optics. So he's saying, like, we kind of already know what should happen with this, based on what we've derived from other experiments. The genuine tests of the prediction of the special relativity can be conducted by the experiments with 2 atomic clocks, or the experiments with fiber Sagnac interferometers. In this paper, we presented a new way to examine the principle of relativity. The principle of relativity of special relativity states that the laws of physics are the same for all observers in uniform translatory motion, regardless of their different motion statuses. Therefore, the phenomena must be the same in these 2 cases: a moving vacuum tube with stationary source and receiver, and a stationary vacuum tube with a moving source and receiver. We conducted the analyses based on optics, and therefore this way is solid by analysis. We also indicated the possible experiments. Obviously, these 2 cases represent 2 different moving statuses relative to the Earth. The proposed experiments are the first-order measurements examining the principle of relativity in 2 systems. So here is just a bunch of experiments that they propose. Just a bunch of ways you could verify or not verify relativity, debunk it. If we have observers 1 on the group of optical media and observer 2 on the receiver, for these 2 observers in uniform transitory motion, they won't be able to identify the difference between the 2 cases. So then we have here with so we've got glass here, then you've got a vacuum cell, so that way you can do the math to derive the lengths here, and you can find not only the difference between the moving source and receiver versus the moving medium, but also you can find the difference of how much the refractive index is relative to that. And he has different lengths he proposes, different lengths of glass, different lengths of vacuum. Yeah. Here is the atomic clocks being introduced to the situation. And yeah. So this one is occurring across the air. And there's a little tiny piece of stationary glass fiber in there. Just a bunch of ways to, doing all these together, you could then derive the math to, find how much the refractive index is being taken into account with this as well. More experiments. This one uses a loop instead of atomic clocks. For some reason it's tiny. And then this one has stationary non-dispersive medium. So just moving the whole thing of medium, or just moving the source and the receiver, and then you can tell the difference. And then here we have non-dispersive medium, non-dispersive fiber, then we have a fiber optic coil. You can move the coil, you can move the clocks. You could have a whole bunch of fun. So, in conclusion, we find not only delta R2 is not equal to delta T2, but also delta T is not equal, or delta tau is not equal to, or I don't know what that is, but in any case, it's not equal to delta T. And that's talking about moving source and receiver versus moving medium. Contrary to what the principle of special relativity predicts, it is clear that the difference between them is that one has a factor n minus 1 and the other has a factor n. To examine whether the factor is n or n minus, this is him talking about the refractive index. We can conduct the experiment as shown. Because in these configurations, the non-dispersive medium is stationary and the total propagation time interval in the medium is proportional to the length of the medium, we can greatly increase the total time interval by using a non-dispersive fiber coil with the length L. So that's him explaining why he would use that fiber coil in that other, in this configuration. It's just to increase the amount of time so they can get a larger proportional difference. So that was what he published in 2016, and then in 2023... last year, he just published this one. He published The Anisotropic Propagation Speed of Light on Rotating Earth's Surface, Theoretical Derivation, Implications for Definition of Meter, and Crucial Experiment. And he published this one, again, with his homies in China, or with just Li Zan in China, at the Shanghai Jiao Tong University. And they write, whether the propagation speed of light at the surface of rotating Earth is isotropic or not is both an important theoretical problem and one that has significant implications for scientific practices. The basis that the speed of light is constant, c equals 299792458 meters per second, by applying the GPS range equation, whose correctness has been fully verified by GPS practices, we found that the propagation speed of light on rotating Earth's surface is neither constant nor isotropic. Where that is the local linear velocity of Earth's motion, and d is the unit vector of the light propagation's direction. Based on this finding and the difference between Earth rotation's Sagnac effects on the equator and the meridian, we propose a crucial experiment to examine the anisotropy of the propagation light speed. So he's saying it's not the same one way or the other. A meter, according to your speed of light meter, is different one way than the other. So let's let a stable pulsed laser emitting pulses in two opposite directions use the ultra-fast imaging techniques for visualizing, measuring, and comparing the spacing of the pulses in opposite directions, and then we can decisively conclude whether the speed of light is anisotropic or not. So you'd use ultra-fast imaging on the receiving end, and you would just essentially send pulses in both directions. So the vast majority of people believe that in the Earth system, especially on the Earth's surface, where experiments are easier to perform, the one-way speed of light in a vacuum is constant and isotropic. But there are just a number of experiments that claim to show with high degree of precision that the propagation speed on the Earth's surface is isotropic. However, a closer analysis of these experiments reveals that they have one thing in common. The light beam is reflected back and forth many, many times, meaning that no experiment has ever really tested whether the one-way propagation speed of light is isotropic on the rotating Earth. Therefore, the claim that the propagation speed of light at the surface of the rotating Earth is isotropic has neither a theoretical basis nor experimental verification. The Sagnac effect caused by rotation is the basis for fiber optic gyroscopes and ring laser gyroscopes that measure all rotations, including the rotation of the Earth. And in the two-way satellite time and frequency transmitter, using the propagation of electromagnetic waves among satellites and ground stations, we can clearly find the directionality of the Sagnac effect caused by the Earth's rotation. In this paper, we analyze the propagation of light between two adjacent points on the Earth's surface using the GPS range equation. We found that the propagation speed of light on Earth's surface is neither constant nor isotropic. The propagation speed of light is c prime equals c minus VRE cosine, what is that called again? Theta? Where VRE is the local linear velocity of rotation on the Earth. So he's just showing you here the calculation is straight up linear. You don't need to include rotation in any way, shape, or form. But yeah, so I mean, it just implies an isotropy. It's not, the speed of light is not the same in both directions. It's different east to west and west to east. And here he is.
That's theta.
Thank you, sir. So cosine theta. A light wave propagates from A to B, and both A and B are co-moving with the same velocity, VRE. So he's showing how the rotational vector, is how we measure linear vectors on what they call a rotational vector. So let us discuss a very important implication in physics caused by the anisotropy of the propagation speed of light on the Earth's surface. The implications of the anisotropic propagation of speed on the definition of a meter. Length is the first fundamental quantity in physics. It is well known since 1983, the unit of length, a meter, is defined as the length of a path traveled by light in vacuum during a time interval of 1 divided by 299792458 of a second. Obviously, this definition requires that the speed of light in a vacuum be exactly the constant at any time, anywhere, in any direction. However, as we know from the theoretical analysis in the previous section, on the Earth's surface, where we primarily use the definition of a meter, the propagation speed of light is not a constant, and it is anisotropic. This apparently destroys the basis of the definition of a meter, thus making the important fundamental quantity in physics, the length, one that bears the errors. So just because we don't want to be moving in, just because we want to be moving in space and we don't want to be the center of everything, the length of a meter is different one way than the other when when you scale it to the speed of light. Crazy. But let us make the problem more specific. Since a meter is defined that way, we can make a light ruler similar to a tape measure. A pulse laser emits a beam with a pulse period of 1 divided by those many seconds, and an ultra-short pulse duration, example given of 0.3 picoseconds. Then the distance of the spatial separation between two pulses is 1 meter, and we call it the light pulse ruler, LPR. And that was all my highlights from that paper. So we have now gone through all 12 of his papers. And so I think it kind of tells a story of somebody that had an inkling about something, started studying it, studied so hard, he came to America and kept studying it. He published about it in China, came to America and published. To cross the world and challenge relativity is, I would say, quite admirable. And that's what he did. He crossed the world. He came to America and he challenged relativity. And he had an inkling about something. He started looking into GPS. He started reaching out to people. He started, looking into where to research. And he looked under the covers or under the hood of GPS and saw what we've been talking about, that there's a relational proportional velocity of the crafts, and that it's not in line with relativity. It contradicts relativity. And so he started writing about it, and he started thinking about it, and he came up with this speedometer idea, and then he got it patented, and then he showed it again, and then he kept writing about it in other ways in which he could debunk the people that are trying to make up apologetics for what he showed, because people are religiously attached to relativity, and so that's why this guy is a heretic, literally. Like people will talk about Wang like he's a heretic. And my hat goes off to him, because he put a lot of obviously he did a lot, and I think it's quite a story. I think the fact that anyone would try and tell you that it was an unremarkable experiment or that he was doing some kind of a parlor trick does not seem to be paying attention to the actual work that he did, because he's quite thorough. And so I will close with another quote from Robert Bennett from the same paper, A Landmark Experiment, the linear Sanyaka test of Wang. The lab frame is the absolute preferred required frame for applying the laws of motion. The Earth is always dynamically at rest. The primitive substance of ether that fills all space can be forced to move, has flexibility, by mass in motion through it. So, yeah. Thank you, everyone, for being here. Does anyone have any thoughts or questions?
Dude,
That was awesome.
amazing presentation. And to to touch on that last part about the Earth being dynamically at rest, that is, the most important part of this, really, because the interpretation of these results, how to interpret them, all comes back to, where is that absolute rest at anyway, right? That one of these velocity vectors is able to be referenced against, right? Well, it's the Earth, right? Where the laws of physics were all derived, right? Everything has to be dynamically covariant with the rest frame, boys. Not the slightly rotating, but just locally inertial enough to conduct any experiment, right? Actually at rest, that's it. It's so when you're like, oh God, they've done such a number on us with the kinematics and dynamics, man. So that's a very, very important part of it, man. How do we even interpret these results? Do we, that's it right there. So having that framework and understanding that is huge to this.
Yeah, it probably would have been a good idea to have brought up Tartaglia and then, Boudra, those explanations as well. But this was kind of all about more about Wang. We could go into those another time.
We could touch on them real quick. It's a
Sure.
easy steal, man. Yeah, so they actually actually invoke absolute space to describe it, which is what Einstein explicitly says his theory, it doesn't need to do to explain it. So what they do is they invoke a geometrically convenient position. Now, usually when they talk about this with the Earth, they'll say, "Oh, okay, we'll invoke it with respect to the fixed stars." But to do that for a locally rotating Sagnac device would be a bit absurd, right? So what they do is they just, invoke your boy imaginary, convenient, geometrically symmetrical position at the center of the axis of rotation, and then they put the observer at the rim of the rotating device, right? And they say that there's a time difference between these two gentlemen, and that time, and there is, right? But can that explain a fringe pattern difference that's proportional to the velocity of the rotating device? Well, no, it can't, because if it could, or no, it can't, because it wouldn't produce a fringe pattern if the speed of light was the same, right? It would recombine and it wouldn't produce a fringe at the other end, right? So they can't actually invoke that as an explanation for the time difference. The physical fringe pattern, the fact that there's a physical displacement that's measured that gives them the proportional velocity, completely falsifies the notion of like, well, we can just get the geometrically convenient position with respect to the stars or the center of the rotating thing or whatever we really need to. Nah, sorry, it's not enough.
The center of the rotating thing. Oh, I mean, this will prepare them for when they try to do the nonsense stuff of splitting frames and applying things selectively, independently, whatever they have to do to fix it later, right? So this will prepare people for the nonsense that they're going to try and have to do to get out of what they already have.
Yep.
Yeah. It's like I would kind of reiterate what I said earlier about how there was that point where.
Hey, Toby, your mic's maybe move it a little further away. It's a little distorted.
A little sharp, a little hot.
A little sharp, yeah. That's a good word.
Yeah. There you go.
So yeah, when you get confused, it's almost 90% of the time when it comes to this stuff, it's because you're being gaslit. Like, it's just
that makes sense.
It's confusing by nature because they want you to feel like you don't understand it, because then you'll see how stupid it is, essentially. And every time every time that I start feeling like I don't understand what's going on, or at least when I'm like debating people about this, it's usually because I'm giving them too much credit, and then I realize later on, like, oh no, that's like the dumbest thing. What they're actually arguing there is, well, usually it violates relativity directly, right? But yeah.
Dude, if you ever find yourself like Lorentz contract transforming things in your own everyday existence, just think about what you're doing. You're like, okay, I'm applying this transformation because all space and time backwards compatibly shifted. I'll never be able to tell or notice, but I want to make sure that's accounted for in whatever I'm doing.
Yep.
You should feel retarded if you have to do that, okay?
Yes, that is that.
I watch dogs translate themselves back and forth all day between the reference frames, but before recognizing one is primary, meaning you can't relativistically shift back and forth with no meaning, right?
Exactly. Yeah, that's such a perfect point. Like, they literally have their paper literally just has to Lorentz transform what happened right in front of their faces. And, it's easier to get away with when it says relative to the sun and stuff, because that's all in your brain anyways, fantasy land anyways. So when you add more fantasy to that, you don't realize the trick as much. But when you do it with something right in front of your face that you just measured, directly proportional, it's like you're getting quite religious there. I mean, it's already religious, but you don't realize it, at least. But yeah, in any case, great point. Anyone else? Any thoughts, questions? Cool. Well, I'm going to go ahead and close.
I think we needed this.
Yeah, I think it's good because I think the timeline is good with him, because it really shows that he wasn't just messing around.
Very thorough, different methods, all verified, the same thing. You cannot possibly say it hasn't been generalized unless you choose to misinterpret reality, which I guess allowed to do.
Yep. Well,
I can't say you can't, right? That's so frustrating because I guess it's technically allowed.
I'm not going to force you to acknowledge the linearization.
just admit I won. Yeah.
I won't make you do it, bro.
No, I won. You will concede. You're not. We will not end. We will not end this stream until you concede.
Yeah, baby. Good game.
So the way that I interpret the final one from 2023, he's like been sitting there for so many years, and he's thinking, what in the world could we do to make them actually acknowledge? He's like, oh, I'll point out that we can't even use a meter. That's literally why he did it. Bro. I bet money. He's just like this. I mean, he's like frustrated. So he's like, okay, I mean, I'll bring up anything I can that may make them actually acknowledge it.
That's I hope to be very effective, right? To have that hit home, but I can see dogs being like, "I'll just switch to a foot."
No, they backfire, right? They're like, oh well, we definitely can't change it now. Like,
Yeah, once they made it their ruler, man, they can't go back on it, right? That's why it's so pivotal, because all their distances that they get, that they're trying to describe for things in the sky, especially in particular, right? That's all based on a fixed speed. Like the mythology based around that is what gives them the leadway to say absurdities like, "Oh, the parallax is measuring a star that's 60 quadrillion zillion miles away because light just travels forever like that at that speed."
But half the other way in the different speed. Don't worry about that. It's fine.
Cool.
Dunking. Yeah.
Well, I'm going to close my stream out then.
Yeah, cool. We'll go ahead and end it on that.
Sounds great. All right. Thanks, y'all, for tuning in. And we'll see you all on Thursday for research and reading night. I do not think we know our exact topic or paper yet, but we'll get that figured out probably within the next 24 hours here, I would assume. Or maybe now. Anyone have any ideas? Shane, Alan, anyone?
How far did you guys get with the Æther Dynamics paper? Did you finish that?
We did.
Oh, Æther Dynamics one. Which
You're
one?
talking? Are you talking about the
one.
book?